A set is a collection of distinct objects called elements. So, for example, this here, and it's common to denote sets with these curly brackets. This is a set with 3 elements. So here, this whole thing is the set, and each one of these is an object, which is called an element. So here, this is the set with 1, 2, and 3. And so one way that we can talk about the objects belonging to the set is with this notation. So we'll say that 1 belongs to the set 1, 2, and 3. And for example, for the set 1, 5, we will say that, let's say, 4 does not belong to this set. So this is how we talk about objects that belong or do not belong to sets, right? And so here we see one way of denoting sets, and this is called the roster notation. And it's where you essentially just list out every object in the set. So here, for example, of course, you have 1, 2, 3, but you could have A, E, I, O, U, but you could also have any other kind of things. You could have names and combined with numbers, and this is the set A. You can also have a set that has sets in it, right? So this could be the set that has the set 1, 2, and 3, and the name Alex in it, and so on. So lots of combinations can be done. Lots of different sets can be created, right? So another way of denoting sets, and this is often needed when you talk about infinite sets or sets that are too big, is something called set builder notation. And so the way that a set builder notation works is you put the curly brackets and then you write it as all the elements in some other set such that, so this is how you read the 2 dots here, such that some property holds. So in this case, such that n is even, right? So let's write that up here and look at it a little bit more carefully. So if we look at the set n belonging to the integers, and we'll see later, so this is the set of integers, such that n is even. So this corresponds, if we were to sort of list out, of course, hard to list out, how do you say, infinite number of things, but this would correspond, let's say, to having 0, 2, minus 2, 4, minus 4, and so on. So this is an infinite list with all the even integers, and you can see that this is a very compact and good way of essentially denoting this. Here we're sort of assuming that we understand how we can extend this, but in principle there could be so many ways that this could be extended. Why do you have to continue with the even integers? So this is just very precise, right? Another example is this set here. So this would be all the numbers that are real numbers such that their square are less than 4. So essentially this is gonna be all the real numbers in between minus 2 and 2, right? Because those are the numbers that give you square root x squared less than 4, right? And so on. So you can build a bunch of other sets. And so let's talk about some few important details. So first, order does not matter. So here, the set 1, 2 is the same as the set 2, 1. So in sets, we don't really care about the order in which you write stuff, which is different than a vector, right? When you're doing linear algebra, if you write out a vector 1, 2, right, it actually is an ordered list, so you do care about the order in which things appear. The other thing is that repetitions do not matter. So if you have the set 1, 2 and the set 2, 1, 1, they are the same thing because the repetition of 1 doesn't really matter. A set The only thing that matters to a set is what are the objects that it is made of. So this set here is made of 1 and 2, and that's it. And so this set here is also made of 1 and 2, and just adding a bunch of repetitions or changing stuff doesn't change anything. So one way you can think about a set is it's like a bag that you put stuff inside, and so it doesn't really matter what order things are inside. The only thing you want to know is what is in the bag. Just that, right? Now, another thing is let's talk about two important sets that come up. So one of them is the empty set. So the empty set, very important set, is the set that has no elements. So it's the bag that has nothing inside of it, right? And this will be relevant for many things that we'll see later on. And so this is quite an important set. So the bag with nothing, that's the empty set. And then you have, in many contexts, you have something called the universal set. So the universal set is going to be context dependent. So this depends on the context of what you're talking about. And sort of in the same way that in when we were talking about logic, we had that universe of discourse. So there are contexts in which you want to have sort of a universe of sets that you're talking about, and then everything is with respect to that. So it's some form of how do you say, like if you're working over all the integers, maybe your universal set is the integers, and then you're interested in looking at subsets of the integers like this, and we'll talk about subsets later, but essentially sets that are inside of the integers and so on. So the universal set tells us what objects are being considered in the background, essentially. And like we said, it'll be context dependent.